Well, let's do lab 12. This one, this one is a little more sophisticated than the one where you spun the cork around in a circle over your head. This is kind of more of a grown-up lab. The idea is to measure the gravitation constant, the capital G, that appears in Newton's inverse square law. The way we do that is to measure the force between known masses that are a known distance apart, which is, of course, a very sensitive measurement. Gravitational forces are reasonably large when you're talking about planetary amounts of mass, but masses you can hold in your hand or stick in your pocket, the forces get pretty small. But we can measure it with, I should probably get you a little closer. Got a torsion balance, invented a couple of hundred years ago by Henry Cavendish. I should probably get the monitor turned so I can see what I'm doing here. So you've got these two large masses outside the apparatus. This one and then the other one over there. And then inside of it, all kind of tilted sideways, maybe I should do it this way. It's all enclosed because of if you had any air currents, the balance would never stabilize enough to read anything. But inside of there and there are two small masses. I think they're only like 20 grams or something like that. It's written down in your lab sheet. They are on the ends of a horizontal rod, which is suspended from, this probably will not show up terribly well in the video, but can I see that? Actually, yes, I can just barely see it on the monitor there, so maybe it is going to show up from up here all the way down to there. There is a hair-like strand of metal. It's like only 1/10 of a millimeter thick, and extremely easy to break, by the way. I've had to deal with that a couple of times. So the horizontal rod here, maybe if I just kind of simulate it. So imagine this is the rod inside that Cavendish balance over there. And there's a mass on each end, okay? That hair-like strand of metal is supporting it, okay? It, starts here and goes on up into the top of the thing. And it takes only an extremely small amount of force, well, torque actually, to make the thing turn one way or the other. Twisting such a delicate little strand of metal takes an extremely small amount of torque, small enough that there will be a noticeable deflection just from the gravitational attraction of the smaller masses toward the larger ones, okay? To be able to see how much the balance has moved, there's a mirror. I should set this down again. There's a mirror right there. You can see a bright spot where there's a laser hitting it. And after bouncing off the mirror, the laser goes the length of the table and makes a spot on the wall over here. So just a fraction of a degree of rotation of the apparatus will produce a noticeable amount of movement in that spot. And so that's how we're going to see how much it turns. The other issue is the calibration of it. How much movement of the balance equals how much torque acting on it. this is the reason, and you'll be expected to explain some of this stuff in your write-up when you do it. The reason that you need to measure the period of oscillation is to determine the stiffness of that strand, okay? Once I get the thing disturbed, that horizontal rod with the small masses on the end is going to twist back and forth over and over again, but a lot slower than this. The period's around 10 minutes. I intend to use the pause button rather generously in this lab so that you aren't sitting there, falling asleep or something like that. But doing this lab in person is a little bit like watching grass grow. Well, it's not quite that bad, but the idea is, here, just a second. The idea is, and this was covered in section 10, the section on harmonic motion, but the stiffer an oscillator, the shorter its period. Easy to illustrate with, for example, these two rulers here. The plastic one is very floppy, the wooden one not so floppy. And notice that if I set them vibrating, the period of the one that's not very stiff, that has a relatively long period compared to the period of the stiffer one, which is just a tiny fraction of a second. I did that once a few years ago and broke the ruler. These things happen. Anyhow, so that's why we need to time the period, is the period will tell us how stiff the strand is that the balance hangs from. And the stiffness is basically how much, how much turning it corresponds to how much torque. Okay, what angle corresponds to how much torque? That's what the stiffness is. And then how much it turns, we measure by how far the spot moves across the wall. And I think that pretty much covers how the thing works. So to begin with, the first blank on the answer sheet, this is one of those answer sheets that was hardly worth the trouble of duplicating because there's only a couple of blanks on it. But R means the distance from the mirror to the spot on the wall. So I have laid out a convenient tape measure along the, where's the wall? Okay, starts there at the wall, goes along the tape measure, or goes along the table, and probably making everybody seasick. But this could be off by a centimeter or two because I don't have the tape measure really close to the mirror. But that is not going to be the major source of uncertainty in this experiment, so let's not worry about it. It looks like, just kind of eyeballing things, it looks like I've got the front edge of this ruler pretty much underneath where the mirror is. And we've got, right there is 3 meters plus another, might as well call it 31 centimeters. So 3.31 meters for R. Now here's where I should start reading the directions. Procedure. 1, measure R, did that. Number 2, actually I think I've revised, this is the version of the lab from 2016. I think I've rephrased a little bit of this here and there in the current version of it. But whatever number it is in the directions, it says tape a strip of paper 4 or 5 feet long to the wall so the spot will move along it. So there's the spot, and about there to about that would be about the right length. Oh, that's clever. I put a twist in. Fortunately, tape is cheap. That looks a little better. Let's give it a little support in the middle just for good measure. And I should have a pencil handy. I'm going to want that. Oh, looks like you got turned around. Here I am over here. Okay, tape the paper 4 or 5 feet long to the wall, which you may or may not have just seen me do, but there it is. Probably should have paused it for that too. Have the instructor gently move the masses until they touch the glass in the before position. So here goes with that. But see, right now, where's my ruler again? Right now, the mass over on this side is pulling on the end of that rod in one direction. And the mass on the other side, which is over behind the apparatus where you can't really see it right now, that's pulling the other end in the other direction. And that creates a torque which twists it. Well, if I move the masses to reverse the torque, that'll twist it the other way. So okay, I have reversed the torque on the balance. And what we're going to want to do next for quite a while is watch the spot. Which at the moment is there. The spot will begin to move along the wall as the metal strand twists back and forth, very slowly. 2 or 3 minutes, the spot will reverse direction. You need to mark where it does this and start the stopwatch. I'm going to let the camera run until it does that, and then I'm going to start pausing it to save you guys a little time. But it should be headed in that direction, which means I might do well to go sit on the other side of the table. Got my stopwatch right here. The motion of the spot is easier to see if you've got a reference point like that. You see, I've got it. Oh, which side did I say to use in the directions? It doesn't really matter. The right side, okay. Well, anyhow, you can see that that's moving relative to my pencil. That's the balance slowly twisting for the reasons I mentioned. When it eventually turns around, I need to mark that point. I guess we're going to go with the right-hand side of the spot. And at the same time, I need to start the stopwatch. Okay, you see that bouncing around? That's because I just readjusted the chair I'm sitting in because I thought it was too high. And I'm sitting now 3 meters away, from like 10 feet away from that thing. That's apparently I should have been more gentle with the chair, but it's sensitive to vibrations. We actually have an advantage here in this recorded version of the lab, because except when I do foolish things like what I just did with my chair, we don't have the usual sources of vibration. If you've got 20 people in this room moving around, oh yeah, that was me hitting the table with my elbow. Also kind of foolish. That's why it says in the directions that you guys just don't even touch the other half of the table down where the balance is. But anyhow, without 20 other people in the room to constantly, footfalls on the floor and bumping into their tables and so on, we should get results that are a little more free of random noise, unless I keep bumping into things. It should turn around before too much longer, but it looks like we're not quite there yet. Yeah, that's crept over a little more. No, I did not mean, there's no eraser on this. I just made a stray mark. I didn't mean to. Pick up the stopwatch because I'm thinking I might need to start it soon. Yeah, that is starting back. So I'm going to mark that. And the stopwatch is running. And yeah, that mark that was on the right-hand edge is in the middle of the spot now. So it's definitely turned around. So we're supposed to mark this one. Kind of hard to write on this because the wall isn't very smooth. B as in before, and 1 as in the first of the 3 points that we need to mark, with the weights in the, or with the masses in the before position. So, yeah, what happens next is about 5 minutes from now, I'll do the same thing over here. The spot's going to get over in here somewhere, slow down, stop, turn around, and head back. And I have to mark that point B2. And then when it gets back over into, at B2, I leave the clock running. Okay, that's only half a period. I have to let it come back. If it was a simple harmonic oscillator, in other words, if there was no friction, then it would return all the way back to B1. But we have damped harmonic motion here. And so it's going to not go quite as far and it's going to turn around again about here, and that'll be B3. And that's when I stop the stopwatch, and that's when I'll start the camera up again. So I'm going to pause this for about 10 minutes. Well, I'm up to almost 9.5 minutes on the stopwatch. So thought I'd start the recording up again for a minute or two. And once again, we need to have this here for a reference point so that any small amount of movement is noticeable. And it's still creeping to the left, so I'll slide it over a bit. And it's thinking about it. Yeah, I think that's it. So I need to stop the clock. And that's B3. Probably noticed the one that I did over here while it was paused. Yeah, it's going back because that line goes right through the middle of the spot now. So we're going to time it again. This is one of 2 trials for the time, and we'll average them because there's obviously a certain amount of uncertainty as to exactly when that's turned around. And that's what we've got anyhow is 10 minutes, 21 seconds and some change. And the camera insists on focus. Oh, there we go. So now we're down to where it says, have the instructor move the large masses to the after position. All of this have the instructor part is that I don't want people handling the balance because like I said, it's very delicate. And if I've broken it a couple of times, how much hope have you got? So besides, if it breaks, wouldn't you rather I did it? Then we do the same thing over again. So the cord on the camera is caught on something. There we go. That way. Okay. So now I just reverse the torque on the balance by doing this. And now I guess might as well pause it again for a while. Maybe I'll include a few little snapshots in here of what's going on. You can see that the dot has already traveled well out of the range that it was in. You can see B1, B2, and B3. So that's the gravitational pull of those masses acting the other way around on the balance. I think it's still moving toward the right. It was going along pretty quick a minute ago. Yeah, it's still creeping a little bit. Anyhow, I'll pause it again and make the marks and start the clock and all of that. Okay, this should be turning around again pretty soon. So let's keep an eye on it. And this will also be where I need to stop the clock. That moved just a little more. That's it right there. Yeah, there's already starting to be a little gap between my mark and the spot. It's heading back to the left. And here's our second reading for the time. I didn't actually write it down. It was like 10:23 before, wasn't it? A little closer if that helps you see it better. It's got the laser on it. That does not help you to see it better. Anyhow, just under 10 minutes, 17 seconds this time. And the difference, again, is basically my reaction time, trying to judge exactly when that thing is turned around, when it's moving so slowly just before and just after. I think I'll pause it one more time. I'll turn off the laser and lock up the balance, and then we have a couple more measurements to take. So the only thing on this answer sheet that we don't have yet is the distance S. We have to do some work on this paper strip here. Now, S is the distance between where the dot would settle down. You know, if you wanted to wait a couple of hours for the thing to stop swinging back and forth, where would the spot have been with the weights in the one position? And that's assuming it ever stopped swinging back and forth, which is a little questionable. But if you waited long enough, and if we had better vibration isolation so that the thing settled down, it would have been somewhere around here with the masses in the before position. And if we let it settle down with the masses in the after position, the spot would have settled down somewhere around here. And S is the distance between those two equilibrium points. Equilibrium with the masses on one side, equilibrium with the masses on the other side. Now, where would it have settled down on this side? Well, if it was frictionless motion, that would just be the midpoint between where it turns around on the one side and where it turns around on the other side. But it's not quite that simple because the amplitude is decreasing as time passes. Well, at the moment that the spot was here, the same distance to the other side of equilibrium would be halfway between these two marks. So let's see where that is. That, from that mark to that mark, I'm seeing about 2.3 centimeters. So 1.15 would be about there. I don't think it could say to label that. I don't think we need to label that. So then it'd be halfway between here and here is the equilibrium before. How far apart are those marks? I'm thinking 14.2. So 7.1 from either side. Right there. Equilibrium before. Same idea with the after position. Where is halfway between these? Well, that looks like about 2.3. So 1.15 is about there. Is that really centered? That doesn't look right. Oh, that's not 2.3. That's 2.8. Half of that is 1.4. Not that much different, really. But so 1.4, actually, it should be this one. Yeah, that looks more like it's in the middle. So halfway between there and there, we've got, looks to me like 9.5. So 4 3/4, right about there. Equilibrium after. And finally, what the distance S is, but the moment you've all been waiting for, S equals how far from there to there. So I'm seeing, well, it's either 11.7 or 11.8. So if you can't make up your mind, I guess go with 11.75. But that should be all the information you need. Maybe after I stop the recording, I'll recheck and make sure I didn't make any other mistakes reading a ruler. But if I don't start the camera up again, all the numbers looked good after I paused it. And what you have now is a rather lengthy series of calculations to work through. The directions kind of talk you through it step by step. Good luck with that. Okay, it's a good thing I rechecked this. Maybe when I was doing this before, you were all out there in video land screaming, wait, no, stop, but I couldn't hear you. So I think I said 11.75. Yeah, I don't know. The before equilibrium was good. There's that mark over there where it's about 7 centimeters from that one. And from B2 on the other side there, that's also 7 centimeters. So that's centered like it should have been. But for the after position, I don't know where this came from. There's too many marks. I must have measured to the wrong one or something, or maybe it was just temporary insanity. But I think I've got it right now. Let's look one more time. This middle mark here is a little bit, it's like 7.8. It's a little bit less than 8. And the A2 on the other side also a little bit under 8, about 7.8. So from the equilibrium before to the equilibrium afterward, 8.9 centimeters, like it says there, rather than ignore the number I said before. So hopefully I haven't done anything else to mess you up. But the good thing about that is if I have, then you can blame me. Whereas when you do a lab yourself, I can blame you. So, we had the radius was something a little over 3 meters. And the two times were a couple of things that were a little over 10 minutes. And with a little luck, this number here is the hardest one to get right. This is the biggest source of uncertainty, because aside from the fact that you've got a guy who apparently can't read a ruler, you've got this big fuzzy blob of light that you're trying to measure the position of, and it's hopping around while you're trying to do it. And did you mark it at exactly the right time? And so that's got to be, what does it say to do for the uncertainty in that? Probably make some sort of an estimate. Yeah, estimate an uncertainty. But, it's very easy to imagine that being off by, even if I was only off by 0.5 centimeter on this side and 0.5 centimeter on that side, between those, you could be off by a whole centimeter, and that would not be surprising at all. So I think that takes care of it, and I'll stop it here.